Good afternoon, everyone, and welcome to today's webinar titled How to Evaluate Viscosity, FTIR and ANBN Results from Oil Analysis Reports. My name is Taylor Colon, and I'm a Customer Engagement Specialist at TestOil. I will be your host today. Before we get started, there are a few things I wanted to go over. First, everyone is muted. We are recording today's presentation, and by being on mute, this will ensure high-quality recording. Second, please feel free to use the questions box in the GoToWebinar application. We would be happy to answer any questions that you may have. Finally, the webinar recording will be distributed later today along with a survey. Look for that in the email you registered with. Let's get started. Today's webinar is presented by Evan Zabowski. Evan is a certified lubrication specialist with diplomas in chemical engineering, registered CET with ACET, and fourth class power engineering. He has extensive experience training tradesmen and professionals in a variety of fields, including lubrication fundamentals, contamination control, condition monitoring, RCM, FMEA, and used oil analysis. Evan has been a member of STLE for over 18 years, serving as chair of the Alberta section for 8 years, and also as an instructor for the condition monitoring course at STLE annual meetings. He also serves as a senior tech advisor at TestOil. Currently, he is serving his 8th year as editor of TLT magazine and was the editor for the STLE Alberta section Basic Handbook of Lubrication. Evan, if you are ready, I will pass the controls over to you.
Great, thanks, Taylor. So as he said, today's presentation we're going to be discussing just a few tests, and basically how they shake out is that when we look at all the tests that are being covered within this series of webinars, we're focused today on the most basic of the fluid properties tests. So we'll cover those today, and some of the other ones have been covered already, and there are future webinars covering some of the other tests. So if you're interested, just look on our website under webinars. Now with each one of these tests, what I intend to do is cover the scope and significance, generally quoting from ASTM what these tests are intended to tell you. Then I will give in layman's terms a basic principle of the test. How do you arrive at the result? What is entailed in the testing? And from that we will learn if there are any limitations or interferences regarding accuracy of the number that you're going to get out of the test. And where possible, I will try and provide you with precision and bias figures. This helps us understand just to what degree can we read into the results. Is this a number that it changes on the first decimal place or second decimal place simply because of noise on the instrument, error within the method? Or can we actually read into those changes as actual variables happening within the lubricated system? Once I cover that little bit of preamble for each of the tests, I will get into the results. The format is to cover the most common cause, at least within my experience, as to why that number might change up or down, and describe, if possible, why it's doing that. What's the mechanism behind it, and what other data do you look at to confirm that that seems to be the likeliest answer? Once I go over the most common cause, I'll give any exceptions if they're applicable. And one of my favorite sections is any pitfalls. How do we misinterpret the number? How do we assume something that might not necessarily be true? So with that, I'll get started with FTIR first. So right from ASTM, it does identify the scope as monitoring additive depletion and contaminants primarily. It can cover base stock degradation. That appears in multiple forms. Some of them will look like combustion byproducts as well. So depending on if we're pulling from an engine or pulling from any other type of industrial application, we may see the same parameters on the report, but what they're hinting at may be a little bit different. Now the significance of this test is that we know through elemental spectroscopy we can get a pretty decent look at the wear metals in there. But we don't see any degradation, and contamination, though we may identify some contamination like dust, dirt, and maybe coolant, we can't identify other types of contaminants such as water or any sort of degradation mechanisms creating insoluble materials. So this test provides a quick view of some additional information that elemental spectroscopy does not provide, but complements it quite well. Now, the basic principle of FTIR testing is that we take a very thin film of a static sample, so this is a non-moving sample, and we should simply shine an infrared beam through this thin film and aim it at a detector. Now, as the infrared beam passes through the thin film of material, it's a broad spectrum FTIR. It covers a reasonable range of wavelengths. Some of those wavelengths will be absorbed. So what we measure is the absorbance of certain wavelengths. And the quick little graphic off to the side just gives an example of what one of the spectrums might look like. Some of those peaks are expected to be there because they represent the base stock. Some of the peaks may represent certain additives. As you start to see a used sample, some of those peaks will shrink, and therefore we'll know that some of those additives may be depleting or degrading. But then we'll get some additional peaks appearing, which indicates contamination or mixtures of different fluids perhaps. And by measuring all these different wavelengths, we can identify how much of what is in the oil and report it back to you. Now, the units of measurement are in absorbance per centimeter, which is not an intuitive unit. It's not something most people really worry about. So generally, FTIR results are treated as rather unitless. We don't really concern ourselves with the units unless we're converting it over to something more practical like a percentage. And soot is often reported as a percentage rather than absorbance, simply because it makes more sense to look at a value in that regard. Now, the limitation to this test is that if you want to measure certain properties like acid number, base number, water, fuel, or glycol content, you need to build a multi-point calibration curve to do so, meaning that we need at least 5 samples of different levels of whatever parameter you're looking at, and we run them according to normal ASTM testing and run them on FTIR, and then we create a calibration curve, and it will identify anything within that curve. Meaning if you change the oil type or if your values are substantially lower or higher than how we calibrated the instrument, the accuracy is going to suffer. So to that end, typically you don't see too many labs performing all of these parameters on all of their samples. They will do it for a handful of customers and only on a few of the parameters. In terms of interferences, moisture content plays a significant role in some of the wavelengths that are being measured. Basically, with high water content, you get a giant peak that overlaps a bunch of other peaks and essentially masks them, makes it look like there's a lot more of some things that aren't necessarily there. It's just a giant water peak over top of it. And again, without building a proper calibration, you wouldn't trust the water content necessarily from the FTIR results. You'd rather see it from a Carl Fisher. But these are the known issues with the test. They're not significant. It's a pretty decent test otherwise. If we look at the precision and bias statements, there is not an ASTM method specific to all parameters. Rather, there are individual ASTM methods for different parameters. Now, these 4 are the published ones, so I can quote them quite readily. As you can see that every one of them has a precision and bias statement of less than 1 unit of measurement with a 95% confidence rate. So typically the numbers are reported as whole numbers. They're not reported with decimal values, and this test is accurate into the decimal values. So yes, you can look at a change in results as being a realistic evaluation of what's going on in the system. That's the long and the short of it, though you don't necessarily see ASTM procedures for each and every parameter that are reported. Now, taking that first one, oxidation. What's the most common cause for oxidation values to increase? Well, it's going to be basically a degradation mechanism, which is driven mostly by time and temperature. So the longer the oil is in service, the more you expect it to degrade. The higher the temperature that it operates at, the faster you expect it to degrade. Now, there is a common statement that's made out there, so let's clarify that. But the common statement is something along the lines of the rate of oxidation doubles with every 10 degrees Celsius, 18 degree Fahrenheit rise in temperature. Where this comes from is a chemist by the name of Arrhenius discovered this, that all chemical reactions double with that temperature increase. This is significant at room temperatures and higher. Generally, once we get below room temperatures, the values we're dealing with are so small they're not to be terribly significant. Some references will state that this is not actually even significant until it hits somewhere around 70 degrees Celsius or 160 degrees Fahrenheit, that you're doubling such a small value is not really noticeable. But point being, the higher the temperature, the faster it will degrade. So if your bulk oil temperature is increasing for whatever reason, understand you will expect to see more oxidation within the same time frame. Now, one thing I like to point out about the degradation is that there's such a thing as what I like to call low-high versus high-high. If you just have moderately high temperatures, you will see an increase in the oxidation value only. If you see extraordinarily high temperatures, even just a high thermal event within the system, you will not only get high oxidation, but you'll also get high nitration. So basically, by correlating oxidation with nitration, you can get an idea as to the severity of the temperature that is creating this thermal event or degradation mechanism. It doesn't necessarily tell you how bad it is. That's going to be based off of how high the oxidation result is getting. But in terms of what the mechanism is, and if it's a particularly high temperature, which would mean a very significant starvation of lubricant, or otherwise a hot spot within the system created by friction, combustion, or lack of oil flow. So these are kind of your balancing checks, if you will, as to what your oxidation is telling you. One of the pitfalls, though, with oxidation is that a lot of folks don't know what it looks like. So if you're trying to do a visual inspection on a system and you notice a darkening of fluid, how do you know if it's oxidation versus it's nitration or some other contaminant? Oxidation tends to take on a very, very dark color. It may be perceived as a dark, dark brown or even black. But the other aspect to it is it tends to be crystalline. It's a bit gritty. So if you notice any deposits building up and you wouldn't describe them as being slimy or slippery, but you would describe them as being a bit gritty, chances are you're looking at deposits from an oxidation reaction. And the worse your oxidation is, or the longer you allow it to continue, the greater the likelihood is that it will form such deposits. The picture you see here, this is a reasonably common occurrence that happens in systems that are heavily oxidized, but basically what happens is that it plugs up the oil pickups, the suction that's driving the supply to the oil system, which in turn generally causes a decrease in the cooling capacity that the oil is providing, which conversely increases the temperature, and basically this is a self-perpetuating mechanism. So the worse it gets, the faster it gets worse, or snowball effect, whatever you want to call it. Moving on to nitration. Nitration is also a degradation mechanism. It is also driven by time and temperature. One of the things to note about nitration is that as we have this degradation mechanism occur, generally speaking, you will see an increase in viscosity and acid number. You don't necessarily see an appreciable change in viscosity and acid number with oxidation, but you will see it probably a little bit higher with nitration. And only because nitration tends to indicate a more severe form of degradation. Now, if it's not necessarily a temperature-related issue or a time-related issue, if it seems to be occurring faster than normal, and you can't attribute it to temperature, one of the other driving factors to nitration would be something like microdieseling. Nitration tends to be a combustion byproduct, and microdieseling is a form of combustion that it can occur within a lubricated system. Basically, anything that has oil going from low to high pressure and back again has the capacity to cause adiabatic compression. So whether this is a rolling element bearing or if it's a pump, you may see that any microbubbles that are in the oil stream, as they get compressed, they will be compressed to the point of combustion. When they combust, it is what we call microdieseling, because it is the dieseling effect. But we call it micro because these are tiny, tiny little bubbles. So you're not going to hear this like cavitation or something similar. It's going to be very hard to detect acoustically without an instrument. But what you will see is through the dieseling of little micro bubbles of oil, little micro bubbles of air, the surrounding oil to that micro bubble will be combusted or cooked at least. And this causes a rapid darkening of the fluid and creates some of these nitration-like deposits. If we're dealing with a combustion system, the timing being advanced can lead to greater nitration. And this was an interesting side effect that was noticed in particular by Dr. Barry Hertz from the University of Saskatchewan. They did a study on biodiesel in transit buses. And biodiesel was being investigated because obviously if you have heard anything about biodiesel, it's that it has better emissions and to some point better fuel economy. They found that when they took buses that had been normally running diesel fuel and switched over to biodiesel, in fact they produced worse emissions and had less fuel economy. But by retarding the timing 1 degree only, they suddenly achieved slightly better fuel economy than previously and far, far better emissions. And it was discovered that this nitration effect is significant depending on the timing of the engine. So nitration is one of those things that we don't like to see because it indicates something not right happening within the system. Oxidation, typically you're going to get no matter what, so we don't get too excited by the simple presence of it, but nitration tends to indicate a worse occurrence. Now the pitfall with nitration is most folks don't know what nitration looks like either. Nitration is the stuff that we would call slimy or slippery. It takes on a Vaseline-like consistency, and it tends to be that color that we would describe as reddish brown, or an Indian type red or roan red, whatever name you want to call it. But it is not necessarily a dark, dark color. It will have some undertones of red to it, and that doesn't really make much difference what type of base stock it is. You will typically see just varying shades of this color. The problem with this type of deposit is similar to the oxidation deposit, is that, as you can see in this picture, it is capable of plugging oil pickups and filters. It will block flow, causing a lack of lubrication somewhere else in the system, and again, it could lead to a potential failure. So saying that about oxidation and nitration, one of the other things I'd like to point out is that depending on the method of FTIR that's being used, which sometimes is simply dependent on the application, the type of oil that's being sent in, you may see some other parameters being reported. So just as a quick reference to finish off FTIR, there is another method that is quite common, it's very popular. It's called the JOAP method, J-O-A-P, stands for Joint Oil Analysis Program. It was developed by the military. And what this type of FTIR analysis heavily relies on is a direct reading of the oil, meaning it doesn't necessarily need to see any reference, doesn't need to know what the new oil looks like. It does all of its measures directly off of the lubricant. And the parameters that it reports in, there are several that are mentioned here. So one of the first ones is thermal event acid. This, as you can see, is a degradation mechanism that is triggered by some high temperature event like microdieseling or possibly electrostatic spark discharge. Acids are reported. Now this is not the same as acid number, so it will not necessarily represent the acid number or even correlate that directly with acid number, but it is indication of acids that have dissociated in the oil due to the presence of water. When we say oxidation ester, this is a differentiation in the oxidation mechanism, not that which has caused acids to form as we see above, but that which is causing them to form in the absence of water. So it's a minor difference. It's not to say that if you have high acid that you had high water in the system. It's just the type of acid that's forming compared to the other. Some of the other parameters that are reported are all based on different additives that may or may not be present in the oil. So don't be too surprised if you see some near zero values. This is one of the reasons it's always good to have at least one reference sample so that you know what the oil should have in it. But we measure amine antioxidants, the aromatic additives, the base oil aromatics, and phenolic antioxidants. And from these are all values that will start at some elevated number and deplete towards zero, whereas the first set of values tend to start at near zero values and increase from there. So we've got results moving in two different directions depending on which parameter we're talking about. One quick note about aminic and phenolic antioxidants is that though an oil may have an antioxidant in it, it can have simply an aminic or a phenolic additive, or it can have a little bit of both. ASTM does recommend that if it has both types of antioxidants in it, that you are primarily concerned with the aminic value, not so much the phenolic value. If the phenolic value drops off, this is considered to be okay. It's the more sacrificial of the two additives. It's the aminic value that's providing you the strongest protection and the longest life. So with that, that is the end of FTIR. I'd like to move on to viscosity now. The scope with viscosity is it's a measurement of the resistance to flow for an oil. Why we measure this, the significance is it identifies the grade of product that is there and helps confirm that we are using the correct lubricant and that we have not significantly contaminated it or degraded it to the point where the viscosity is not correct for the application. Now the basic principle with this test is quite simple. We take a sample of oil, we heat it up to the desired temperature, typically 40 or 100 degrees Celsius, and we allow it to flow down a very thin capillary glass tube. We simply time how long it takes to go from one mark to another mark on the same tube, and the longer it takes, the thicker the oil. So by calibrating these tubes, we have a way of correlating the time measurement into a viscosity, and we report the viscosity at the measured temperature. Now do understand that in terms of a thin capillary, the capillary on these tubes is generally around the size of mechanical pencil lead. It is a very, very small bore. So to that end, in terms of limitations, it should come as no surprise that if a sample contains large amounts of debris in it, it may plug the tube or cause a restriction in flow within the tube, therefore either not providing or skewing any data coming from that measurement. So when you have a particularly filthy sample, if it's sampled in a way that's pulling large debris, visible debris, you may expect that the viscosity result is not measurable or at least is not that accurate. In terms of interferences, because we are measuring at 40 and 100 degrees Celsius, it is possible that there may be other products within the lubricant that are volatile at those temperatures, meaning that they may be boiling off or driving out at those temperatures. So water content would be a good one. As an example, 100 degrees Celsius is the boiling point of water. So if a sample has significantly high water content, you may see the water boil as it tries to flow down the tube. Well, if the water is boiling, what's going to happen are steam bubbles are going to try and rise upwards through the tube while the oil is flowing downwards through the same tube. This skews the measurement significantly. It can make it either high or low or just simply an error message. So when we have high water content, your viscosity may not be entirely accurate. That's not considered too big of an issue because that's your problem, water content. Not so much do we have the correct viscosity. We know the viscosity will be affected by that water. The other example that's not quite as common for all folks, but for those who do operate screw compressors, they have a pretty bad history of not getting decent viscosity results. Screw compressors will put the process gas that is being compressed in with the oil, meaning that when you take a sample of the oil, you're going to have some process gas contained within the fluid. So this sets up an interesting argument. We know that these process gases always push down the viscosity value, typically quite significantly. Oils that normally run at 150 centistokes as a new oil value may be half that value in operation due to all the compressed gases in them. So the debate that goes on is it worth degassing the sample to correctly measure the viscosity, or should we measure the viscosity as it contains all these gases because that's what it looks like within the system? There are very much divided camps on this. There are those that like to see the oil degassed so they can confirm that the oil without the gas has nothing going on with it and it's just a gas issue. Others like to see it with the gas in it because they go, well, that is how it is circulating and lubricating. Both offer a reasonably practical answers to which one's better. I've always been of the opinion that it's better to see it as is than it is to doctor the sample in any way. So I'm not a fan of degassing, but it doesn't make me right. If you would like to degas samples so you can confirm the lubricant does look correctly, there are a couple different methods of doing it. One method is to simply let the sample sit. If you let the sample sit for the better part of a week, most of the gases will escape on their own. As long as you leave the lid loose, they'll vent to atmosphere. This is a slow process, and depending on how loose the lid is and what you're doing with it, you may be introducing some contamination to that sample. So for any other measured parameters, it might not be as accurate. The more conventional way of degassing a sample would be through sonication, using an ultrasonic bath similar to how they clean jewelry and tattoo needles and all those other similar applications. High frequency vibration will help shake the bubbles out. This does not tend to affect the sample in any other way as long as it's done briefly, meaning less than 30 seconds worth of sonication. But if you do over-sonicate an oil sample, not only do you remove all the air bubbles, but you will start to break up the particulate. So if you're doing a test like particle count, you will start to skew the results from large particles into smaller particles, and it'll look like a totally different issue. But that is a known interference when it comes to viscosity, is what else is in the fluid and will it boil or otherwise perform some volatile reaction at the temperatures it's being measured. To that end, the precision and bias statements from ASTM for viscosity are given at both 40 and 100 degrees Celsius. You'll notice that they are about 1%, meaning that yes, you can definitely treat changes to the first decimal place as a realistic evaluation of what's going on in the fluid. Trying to read too much into the second decimal place is asking a bit much out of the test. Now, the most common cause for viscosity to change is going to be mixing with something else, whether that is another oil or some other type of contaminant. That will drive the viscosity up or down. So things that cause the viscosity to decrease will be things that have typically a lower viscosity. So a lower viscosity oil, water, fuels, solvents, refrigerants, anything like that will typically depress the viscosity. On the other hand, viscosity can go up if you mix it with something with a higher viscosity, like a thicker oil. But also within this list is glycol. And this tends to raise a few questions. People wonder why, if water has a lower viscosity than oil, how does it depress the viscosity? But glycol, which is also a lower viscosity than oil, cause it to increase. That has everything to do with how readily oils will emulsify. Typically, the thickening effect is due to an emulsification, meaning that we're mixing two things that don't normally want to mix together. And in creating these emulsions, one of the things that happens is you trap a lot of small air bubbles. By trapping a bunch of small air bubbles, you will cause the viscosity to increase. Water doesn't always cause an emulsion. There are many products out there, particularly gear oils and engine oils, that actually contain emulsifiers to help handle the water content and not cause emulsions to form in the sense of with all the microbubbles in them. Other oils out there, like turbine compressor, high-speed pump oils, may contain demulsifiers in them to help keep the water separate. When the water is kept separate, it forms very small droplets. It doesn't tend to form an emulsion, and again, doesn't trap air bubbles. So most of the time that we have water content, we don't see much of a change in viscosity, and when we do, it typically tends to be a decrease when we get to higher levels of water. To be fair, if you got extraordinarily high levels of water, you would cause an emulsion and you would see a viscosity increase, but at that point, that'd be your least concern, and the question would be, where's all the water coming from? Getting back to glycol, though, glycol at even low concentrations will form an emulsion much more readily, and in doing so, it will trap little air bubbles. And that's the reason I've chosen the picture of the soft serve ice cream cone and why I chose the chocolate flavor. I've often joked that a Wendy's Frosty, which is basically chocolate soft serve ice cream, it kind of looks like that picture. That's what glycol in oil looks like. It's even the right color. Glycol in oil forms emulsion very readily. So whenever we know that we have a coolant leak and the glycol is not being boiled off or driven out, you should expect to see an increase in the viscosity to correlate with that. Now, other things that will change the viscosity, and short of mixing with something else, again, going back to oxidation. As we degrade an oil, it will form acids. As it forms acids, it forms other degradation products. These tend to be insoluble and thicker than the base oil viscosity. So slowly but surely, the viscosity will increase over time. If it is a combustion application and we are dealing with a type of compression engine like diesel or gas, you will tend to produce some soot. When we deal with natural gas engines, we don't produce a lot of soot. It would be unexpected to find any significant volume of soot in that type of sample. But gasoline engines, you will see some soot. Diesel engines, you'll see a lot of soot, especially after the 2007 model year when the new EPA regulations kicked in. Soot is not allowed up the stack anymore. Well, they couldn't stop it from being formed, so they simply dump it in the oil. So we've got some fairly high soot content engines out there now. With higher soot content, we can soot load the oil, meaning that we will cause it to turn into a bit of a paste, and you will see the viscosity increase. This tends to be at soot concentrations much higher than, say, 5% soot content. Approaching 10% would be more or less where you'd start to see a significant change in viscosity. Something that can cause the viscosity to go down, though, would be shearing. If it is a high viscosity index product, if it has been additized with a VI improver, it is possible for that VI improver to be sheared mechanically, and as it does so, the oil will revert to its original lower base oil viscosity. Now, shearing tends to be a fairly direct correlation with time, meaning the longer it's in service, the more it will shear until it reaches its maximum shear when it's basically sheared all of the additive. So understand that the longer it's in service, the lower the viscosity will get if there is some shearing occurring. Just because shearing is occurring is not necessarily a bad thing so long as the oil stays within grade. So we shouldn't view all decreases in viscosity that can be attributed to shearing as necessarily negative. So long as within our normal drain interval we stay within grade, it's considered completely tolerable. Now, the pitfalls with viscosity, do remember that with the 40-degree viscosity, if we're talking about ISO-graded oils, industrial oils, we have limits of at least 10% on them because that is the allowance provided by ISO within its own grading system. So you shouldn't alarm anything at less than 10% change because that's just considered par for the course with these oils. So typically we set the first alarm off at anything greater than that 10%, and if it changes by more than 20%, that's when we probably will take some action. The 100-degree viscosity, however, does not have a nice handy grading system or any percentage changes. So you will have to look these values up on your J300 or J306 table and confirm if they are in the correct grade or not. Understand again that these oils tend to be multigrades. Multigrades have VI improvers in them. They are prone to shearing. So typically when you look at a new oil value compared to the grade range, new oils are formulated at the high end of the range, and that allows for some shear to occur without being an issue. If it shears enough that it goes out of grade and into the next grade, that's when you start to be concerned and you will take actions like shortening your drain interval would be one of the simplest solutions. Now, combined with viscosity, it is possible to also get viscosity index. Now, viscosity index is simply a number to represent how much an oil changes viscosity with temperature. So it's just a calculated index. It's a math calculation only. There is no test performed here. The significance of this is it helps confirm if you got mixtures of fluids and or shearing. So if you're trying to select a new oil, you may also look at a viscosity index. It's just a way of evaluating how stable its viscosity is with temperature. The principle of this test, like I said, is just a math calculation. It is based off of a 4-variable equation. Two of the variables are the 40-degree and 100-degree viscosity from viscosity measurements. The other 2 variables are from a lookup table. So in terms of limitations and whatnot, that's all the same as viscosity. So we don't need to discuss that. The most common cause for VI to change would be mixing of products. If you've got more than one product present, they will probably have different VIs. You will get a VI somewhere in between the 2 VIs as an end result. This can happen reasonably commonly because, generally speaking, most sites, if they have 2 oils of the same viscosity, even if they're for the same application, like they're both gear oils or they're both pump oils or something along that line, they probably exist as 2 different lubricants because they will have different VIs. So if somebody accidentally grabs the wrong oil knowing that it's the right type of product and the right viscosity grade for the application, so again, trying to give somebody the benefit of the doubt and saying not doing it maliciously, but if they mix these 2 products, which, you know, from general appearances look like similar if not the same type of product, with different VIs, you will see this reflect in the mixture. It's worth noting that VI, if it ever increases, this is pretty much the only logical explanation. If it decreases, this is one explanation, but of course the other one would be shearing. Shearing causes the VI to go down. Now, something to quickly state about VI for those that did not participate in the Lubrication Fundamentals webinar. Let me go over this real quick. How we make a multigrade, if you were to take something like a 1030 motor oil and ask the average person, how do you make a 1030 motor oil? You often hear answers such as, well, we take some 10, we take some 30, we mix them together, you have a 1030. Well, that is how we make 20s as an example, not how we make 1030s. The next guess that comes up is usually something along the lines of, well, you just take a 30 weight oil and you additize it to behave like a 10 when it's cold. And that's closer to the truth, but it's still not correct. It's in fact the other way around. If you're going to make a 1030 motor oil, you would actually start with the 10, with the lower viscosity base oil. And what you would do is you would additize it with your VI improvers such that the viscosity doesn't decrease as much as it normally would. So by the time it hits the higher temperatures, it actually looks more like the higher viscosity base oil, in this case a 30 weight. So a 1030, as an example, is really a 10W oil additized to behave like a 30, only at elevated temperatures. But this additive, like I said, is prone to shearing, and as you shear it, this is what you should expect. The viscosity will slowly revert back to its original 10W viscosity. So I like to make this abundantly clear because whenever we're checking viscosities and we see both viscosity at 40 and 100 decreasing, that's a pretty strong indication of shearing if you can't attribute it to mixing with another product. As soon as you have the VI, that generally confirms it because you would see a decrease in the VI as well as a decrease in the viscosities, and you would know for a fact it's got to be shearing. But a lot of people mistake increases in viscosity or changes in only one of the two viscosities as shearing. If you're only changing one of the two viscosities, you may be changing the VI, you may even be decreasing the VI, but that's not probably because of shearing, it's probably because of mixing two similar products. So the thing to note about VI is that increases are never due to shearing. Shearing only can ever cause the VI to decrease. If the VI is increasing, it must be being topped up with a higher VI product. It's got to be added in from external sources. The other pitfall is you can't ignore a decrease. The only way for this value to change is by some mechanism occurring, whether that's top up with a lower VI product or if it's shearing. And probably neither is a suitable situation for the lubricated asset. So VI is a great number to monitor, especially if you've got systems that are prone to mixtures of fluids or shearing effects. Now moving on to our last tests, I'd like to talk about acid number and base number kind of together, but there is more than one method I'd like to talk about with acid number. So let me go through two different versions of acid number and then finalize with one version of base number. Now, it doesn't matter which version of acid number we're talking about, the scope and the significance is the same. Both of them state they're there to measure the acidic constituents in the oil. Now, by saying that, understand that there are some things that are in the oil from new that are acidic. Some of the additive package may be acidic. So we're not just measuring degradation acids, we're measuring everything. Now, one of the qualifying statements to this test is that it only measures acids with dissociation constants that are larger than 10 to the minus 9. What this means in layman's terms is it will not measure necessarily weak acids. So years and years ago, about the mid-80s, this test used to be called the total acid number test, or TAN for short. It has not been called that properly anyways for the last 30 years because it doesn't truly measure all the acids, not total acids. So it's just a minor point, but if you do see terminology related to TAN or total acid number, this is the same test. We're just calling it what we should be calling it. Those who call it TAN are just referring to a 30-year-old name. The significance of measuring acid number is that once you know the acid number of the oil from new, any increases from there tend to indicate degradation, and as the oil degrades, you can use this test as a trigger point for a condition-based oil change. Now, saying that there are two different ways of measuring this value, here's the first one. Going by ASTM number, this is what we call D974, or in everyday English, we tend to refer to this one as the colorimetric or color change acid number, because the only difference between the two acid numbers I'm going to discuss is how do you know when the test is over. Both tests use the same solvent to dilute the sample. Both tests use the same titrant to titrate the sample. So with a simple test like this, how you can explain it is basically, if you can remember high school chemistry class, you probably did this test, some variation of it. A titration is when you take something like an acid and something like a base and you mix the two together and you try and neutralize them. If you know how much acid you started with and you measure how much base it takes to neutralize it, by knowing how much base it takes to neutralize it, you know the strength of the acid. So in our case, we measure the sample by mass, so we know how much oil we're starting with. We measure the base in terms of how much it takes to neutralize it, and we know the concentration of the base already. So once we neutralize it, we can figure out the concentration or the value of the acid, or what we call acid number. So in this first variation of acid number, how we find out when the test is over, when the sample has been neutralized, is we add a color changing agent. Now this color change tends to go from a very vibrant orange that you see on the left side of the beaker, and it changes to a very dark green kind of browny color that you see on the right hand side of the beaker. It's very evident when it happens in a nice clean sample like that one. But the limitations to this test is understand that acid number is merely a measure of the level of acidic products within the oil. This can be heavily influenced by the volume of the system. So when we start having large volume systems, we can have very much a diluted value that is not necessarily as volatile or has the resolution and change to properly identify significant oxidation results. Now in terms of interferences, one of the big interferences with this test is if the sample is already starting off as a dark color. When it is dark to begin with, what happens is that it's much harder to see the color change going from the bright color that it should be changing over to the dark color that it's trying to change over to. If it's dark to begin with, it will look dark the whole time. The color change will be much harder to pick up on. The other interference with this test is to do with water content. Basically, if a sample contains high water content, what will happen is during the test, more acids will form. So basically, you end up chasing the answer, and you will tend to skew or bias the results a little on the high side. So this is a known interference with the test. ASTM does recommend measuring the sample twice in these cases, and basically you do it at 2 different speeds. If you do the test faster than normal and you achieve the same result that you did when you do it slowly, then the slow result must be the same. If you do it at 2 different speeds and the faster result is lower, it indicates that the test at the slower speed was dissociating acids while you were doing it, and therefore can be considered to be inaccurate. Now, as for precision and bias, they're represented in this table here. The color change or colorimetric method for acid number has a pretty reasonable accuracy and precision to it. Basically, it's affected at the second decimal place predominantly. Now, the other variation to acid number is really not a whole lot different. It's still a titration. We're still neutralizing it with the exact same chemicals. The only difference is how do we know when the test is over? In this case, we don't measure it with a color change. We measure it with a conductivity meter. We're measuring the potential on the oil sample. So by measuring the potential, we see when there is a change in the potential, and we can identify that inflection point, and what we'll get is a slightly different answer. So to that end, ASTM is pretty clear about comparing results between these 2 tests, and that should not be done, that they will in fact yield significantly different results. So always try and pick the most appropriate acid number test to compare your oil against. So if you're working from a product data sheet, look at the ASTM method number. If it says 974, it is the colorimetric method. If it says 664, it is this potentiometric method that I'm going to talk about. Now, in terms of limitations, it has the same limitation. It may not have the resolution to witness significant changes in oxidation or degradation, as compared to some other tests, and it also has the same interference with water content. What it does not have is any issue with the darkness of the sample. That it can work around quite readily. So this seems like a pretty positive thing, but then you look at the precision and bias statement for potentiometric acid number, and it looks way worse. Well, to be fair to that, when this was last evaluated, it was done using manual titrations, meaning people were doing this by hand. Most commercial labs do this with fully automated equipment that is far more precise than a hand measurement. So what I'm saying to you is these are the published values, but realistically you should expect far better accuracy than what's being presented to you here. Now with either acid number test, understand the greatest cause for the acid number to change is going back to our oxidation values. As the oil degrades, it will form oxidation byproducts. Many of these are acidic. As it forms those acids, they will be picked up by this test. Acid number might correlate with an increase in viscosity. It might not. There are some factors that can cause the viscosity to go down, while oxidation may cause it to go up, and therefore the viscosity will be held relatively stable. You may not notice anything. Like we said previously, one of the things that's going to accelerate how much we form acids is temperature. And that goes back to the Arrhenius equation of every 10 degrees Celsius, 18 degree Fahrenheit rise in temperature. But another factor is water content. Water will cause acids to dissociate from the oil. The higher the water content, the faster we typically form these acids. Many oils have a property that is referred to called hydrolytic stability, and that is how well they stand up to water. And just because you have high water content temporarily doesn't necessarily mean you're going to form significant acids. But if you have persistent water content in the sample, understand that it will help promote the formation of acids, and it will increase exponentially. It's, again, one of those snowball effects. Other than that, the big pitfall with acid number is that to properly interpret an acid number, you must trend it. There is a rule of thumb out there that exists that suggests that when the acid number is double its new oil value, it is time to change the oil. There are far too many exceptions for that to be true. I've given two here depending on what industry you're in, but a natural gas engine oil has a new oil acid number value of about 1. Generally speaking, the OEMs don't recommend a fluid change out till it hits at least 4 or 5. If you deal with rust and oxidation inhibited oils, as in turbine and compressor or high-speed pump oils, typically these have acid numbers of 0.1 or less from new oil. And again, most OEMs don't recommend changing them out until they hit a value of at least 1.0. So you see that there's examples here of anywhere from a 5 to a more than 20 times increase in new oil value before it's time to change the product. So don't try and use that rule of thumb too much. Try and work with your OEM and or your lube supplier to come up with a reasonable cutoff point. If you read into the ASTM standards, they actually tell you how to come up with your own alarm limit for acid number and base number, and that is to simply do it empirically, meaning by experience. So pretty much what you do is you trend it over time. It should be a fairly linear line. The longer it's there, the more acid number will increase and the more base number will decrease. At some point, that rate will increase significantly, and generally you set the oil change to be just ahead of that. The other pitfall with acid number, just to reiterate this one more time, is the larger the volume, the less likely it is for this number to change appreciably. So when we start dealing with large volume reservoirs, understand that acid number is maybe not your go-to test for doing a condition-based oil change. You probably want to balance that with a bunch of other tests, namely other oxidation-specific tests like RPVOT and Ruler. You may wish to also look at any degradation buildup through MPC and ultracentrifuge. Now the last test to discuss is base number. Now base number is really the flip side of acid number. As you read the scope, it says it's there to determine the basic constituents rather than the acidic constituents. So it's obviously pretty clear cut that way. But again, understand that there are some additives that are alkali or basic. Now these tend to be only found in engine oils, so we don't always see them in any other fluids beyond oils specifically designed to operate in diesel engines. most gasoline engines, and even some natural gas engines. The significance of measuring base number is that rather than seeing the damage done, rather than measuring the acids that have formed, you're measuring the ability to help combat these acids. Now, the basic principle is the same. It is a titration. It's not a color change version, it's a potentiometric version. And rather than adding a base to the sample, we add an acid to the sample, but everything else holds the same. Now, the only real limitation to this test is it can only be done on oils that actually have a base number type additive chemistry. If they don't have it, you're going to get a near zero value. Interferences, though, it doesn't have any, because even if there's high water content, as the acids that may dissociate during testing form, they're not going to significantly affect the base number additive. Basically, I try and look at acid number and base number like this. I consider that acid number is a measure of the damage done, base number is a measure of the ability to fight. So I picture these as two different armies of 100 people. And if you were to ask yourself, how can you figure out which side is winning the war? You could do this one of two ways. You could either count the living, which is like counting base number, it's the ability to fight, or you could count the dead, and that is the damage that's done. The side with the most still fighting is the side that's winning. The side with the most that is dead is the side that is losing. So either way, you could figure out which way the battle is going. You do not need to do both, is my point. Typically, you don't measure both acid number and base number. They correlate reasonably directly, so there's not much need to measure it from both sides. You can just measure it from one side. Acid number can be measured on any oil out there. Base number, like I said, predominantly engine oils. The precision and bias statement for base number does look a little goofy because it is an exponent and it's a decimal exponent. So unless you're an absolute math whiz, you're never going to do this in your head. So I've given you a range based on the expected base numbers of 5 to 10. So for any values of 5 to 10, you can see the repeatability works out to around 15 to 20%, whereas the reproducibility is between 35 and 50%. It's not fantastic. It's certainly not as accurate as the colorimetric acid number, but this is pretty much the only method for measuring base number that is done by commercial labs. There is more than one way of doing it, but this is the predominant one. Now, what causes base number to decrease is exactly the same as what causes acid number to increase. So there's no difference here. It's still oxidation. The exceptions are still heat and water content. Nothing is new here. The only thing that really changes, the last thing I have to say, is that the pitfall with base number is that it can only be done on certain oil types. I just want to reiterate that one more time to make sure people aren't going to ask for base number in applications where it's not going to yield them a usable result. So base number can only be done on oils that are actually additized with an alkali or basic additive package. And this, like I said, is predominantly in the combustion engine market. So with that, that concludes the lecture portion of the webinar. I'll take a look here for questions. If there are any, I'll go about answering them. If I'm answering questions, you feel free to keep adding to it and type some more out. So the first question I see says, can we identify the cause of foaming from this test? The test is not mentioned, but of the tests that I have talked about here, no, none of these would really give you a strong idea what is causing oil to foam. The general driver behind foaming of oil, if it is not a mechanical issue, so to cover that off real quick, most foaming problems in my experience, and this is not to say it's always everyone else's experience, but tend to be mechanical related. It's either that the discharge into the reservoir is too high above the surface. It could be that the suction is too close to the surface, meaning that generally speaking that the surface level or the oil level within the tank is too low and it could suck oil in. So whether you're discharging from too high and mixing air in, or you're sucking air in through the suction because the level's too low, that's one mechanism. Another one would be an air leak on the suction side of a pump. That's another great way of detecting a significant foaming problem. Use a smoke pen or something like that and see if you can't tell if there's an air leak, because obviously nothing's leaking out, it's actually air leaking in. If it's not something mechanical like oil level or a leak on the suction side, and you do think it has something to do with the fluid, generally speaking, what that's going to be attributed to is contamination, whether it's water or particulate, something along those lines. So those would be the tests that I'd be looking at first if I was suspecting there was something in the fluid causing the foam to change. Be looking at water content, particle count, maybe a little bit the elemental spectroscopy to see if anything was there. But no, not really FTIR, acid base number, viscosities. Those wouldn't really show anything. The next question says, can an acid number test be replaced by TBN by FTIR? Well, as I said, you could replace these titration tests with FTIR, provided that the FTIR has been calibrated accordingly for that oil type. That's not an issue. Replacing acid number with base number, again, is not an issue so long as there is a base number that can be measured. It's very common for some labs to do base number by FTIR because it is much faster than doing it by titration. But again, not all oils have a base number, so that's why it tends to be restricted to engine oils only. So if you rephrase your question, can you replace acid number with acid number by FTIR? Certainly. Replacing with base number, only if it has the right additive chemistry. And that is the only other question I am seeing. So with that, if there's no further questions, just wait till after the webinar is over. You can always contact us and we'll help answer those questions. But I will turn it back over to Taylor and wrap this up.
All right, thank you so much. All right, thank you everybody for joining us today. And again, we will be emailing you your presentations. You take care.